we start with our first student presenter. Michael Bechard is a candidate for Bachelor of Science in Electrical Engineering, Mathematics, and a minor in Computer Science. So Michael is one of these very unique students that come through the door once in a while. A cumulative average of 4.0 on all of these major concentrations. Last semester, Michael was interning at Raytheon in Sudbury, Mass. And upon finishing with his internship, he was offered a full-time position 1 year before graduating. This is an unprecedented but welcome result for our physics and engineering department here. So it is with great pleasure that I welcome Mr. Michael Bechard to the Dr. John U. Free Seminar Series. The title of this presentation is, instead of flicking a switch, just open the door.
Well, see, the title was going to be called Generating Power from Opening the Door, but I decided to come up with something a little bit more creative. Okay. All right, so like Dr. Conley said, the title of my talk is, instead of flicking a switch, just open the door. There it is. So first I'd like to talk about a little background and motivation. I have a personal interest in renewable energy sources, and of course everyone thinks of solar and wind as energy sources, renewable energy sources, but there are actually lots of other methods out there for capturing energy. And so for a senior project, I wanted to do something with maybe one of these other methods of capturing energy. So before I get too far, I have to remind you that about this time last year, maybe a month or two before this, in February, we had a big hurricane come through, Hurricane Nemo. It dumped 30 inches of snow and knocked the power out for a full 24 hours. So while the power was out, these exit signs, like the one you see there and here, are powered by batteries. Well, after 24 hours, these were all dark. So you're walking around campus, and even inside, all of the lights are out because all of the batteries had died. So I was walking around, and I had a little crank flashlight, which you see here, and it just has a little motor in it that you crank, and then it turns the light on. So I got to thinking, what if you opened the door and that turned the exit sign on, or just some kind of light? So that's where this project got started. So I started doing a little research, and it turns out any DC motor, which is a direct current motor, will work as a generator. So some current implementations of this technique are hybrid brakes. As you brake, it turns the motor, which slows the car down and then generates energy from that. Windmills and water turbines also use the same kind of technique. And motors working in this way are very, very efficient, so we can get a lot of power that's available there. So a little background on how this works. In electrical engineering, we deal a lot with voltage and current. So voltage is it's like a level, and then current is how much is flowing through at that level. So with a typical motor, you put in a voltage, and that gives you a speed, which is usually measured in RPM. And then based on the torque load that you need for the motor, it draws so much current from the motor. So in this case, I'm going to be working that in reverse, using the motor as a generator. So I will be providing a certain speed, and that'll give me a certain voltage, and then based on how much current I need to draw for my LED's power, that'll say how much torque I need to require. So torque is force times distance, which I'll show you a little picture of how I calculated some of that later. Another thing that I researched was light emitting diodes, which are LEDs. A diode only allows current to flow in one direction, so it'll flow one direction and it won't flow the other direction. Light emitting diodes are simply diodes that emit light. They're very efficient. So something for you all to think about, LED bulbs in like a household lamp, the new LED bulbs that you hear about, are powered by 120 volts alternating current. So that means it's flowing one direction and then flowing the other direction. So why are they always late? It's just something for you to think about. All right, so after I did some research, we come up with these initial requirements. The system shall statements, was what came to call them. So first of all, the system shall be able to be installed on any regular hinged door. So any door that you see around here, it just opens and closes, pretty simple. It shall be able to generate power from the door swinging in either direction. So I want to be able to open or close the door and have that generate power. It shall contain an energy storing capacitor within the device itself. So rather than sending power to something in maybe battery or whatever, I just want that built into my own project. It shall contain a low power LED light. I didn't really know at the time what that was going to look like, but I just wanted it to be some kind of LED because I knew those were the most efficient. It shall power an LED or a set of LEDs for at least 2 minutes. At this point, when I came up with these requirements, that was really just kind of a guess. I didn't know if that was attainable. I didn't know if I would overshoot that by a lot. But this was my initial guess, and at the end, I can kind of show you how close I got. The system shall function with no regular maintenance. Mostly what I'm saying there is that it doesn't need like lubrication, or it doesn't need to be charged up or taken care of. It should just work on its own. And last but not least, the system shall start the climb. So maybe that wasn't one of the initial requirements. It somehow found its way in. Okay, after we come up with requirements, we came up with block diagrams. So this is my block diagram. The first block is a swing arm. So that's what's going to connect to the door frame, and then the other end will connect and sit on the gear train or the motor, or however I decide to do that. Block 2 is a gear train because a small motor like one that I could use here is not going to provide nearly high enough voltage at the speed that a door turns at. So I needed to gear that up to get the motor to spin quite a bit faster. Block 3 is the motor, just going to sit on the gear train, and then I'll have some power cords coming out from it. Block 4 is going to be that circuitry, any kind of capacitors that I need, any other circuitry that I need to connect, finally to the LEDs. And the LEDs, again, I didn't really know what those were going to look like at this point, but I just knew that somewhere I need to work that out. Okay. So here's a little bit of research. This is calculating the torque that I could expect from a door. So you can see here, I've got some weights hanging and they're connected to a door hinge. So remember, torque is force times distance. So this weight here is the force, and then the distance from the hinge of the door is the distance. So based on that, and based on the speed at which a typical person opens the door, maybe I was a little optimistic there, I came up with 21 newton meters of torque and 15 to 30 RPMs. So that's what I figured I could work with. So from that, I just started looking for a motor that would work. This first motor that I found is rated at 10 newton meters, so that's about half of what I could expect, which is good. It gets up to 24 volts, that's kind of in the range that I wanted, but it was at 50 RPM. So remember, volts and RPMs are proportional to each other. So if I didn't quite reach 50 RPMs, if I was only at 30, then it wouldn't quite reach 24 volts. It'd be more like 18 or something like that. So I figured that would be okay. A plus on this motor was that it included the necessary gearing, so I wouldn't have to build my own gear train or anything like that. However, this motor didn't really work in reverse just because of the particular gearing that I had. Couldn't spin the motor and get it to turn. It would only work in the correct direction by putting power in and getting the motor to turn from that. I couldn't work with that. Anyways, I ended up sending that motor back. This is the second motor that I got. It's only rated at 0.94 nanometers, or newton meters, which is quite a bit less than the 21 newton meters that I wanted. It's also rated at 24 volts, but only 19 RPM. So that'll be better. That's more in the range of the 15 to 30 that I was expecting. This motor also included the necessary gearing, which was a plus. And this one worked, but the torque capabilities could be better because I could probably provide more than 0.94 newton meters. I ended up going with this motor anyways, just kind of, you know, I already had one motor that didn't work and I wanted to get moving with the project. So the next thing that I worked on was picking some LEDs. I wanted these small, low power LEDs like this, so I just kind of guessed that I would use about 10 to start with. That was just a guess. It just seemed like a good choice at first, and I later modified that a little bit, as you'll see. But I figured 10 was a good guesstimate as to how many I would need. Based on those LEDs, I then picked some, this is the circuitry, so I picked some capacitors. If I were to use all 10 LEDs, I calculated that I need about 0.1 farads in order for the LEDs to be powered for 2 minutes. So I found 4 capacitors at 33,000 microfarads each, which you do the math, and you get 0.132 farads. So that's a little bit more than I said that I wanted, so maybe I'd only use 3 of them, or I didn't really know at that point. But, so then once I got those in, I was trying to figure out, so how am I going to hook these LEDs all up and get them all pointed in one direction and everything? So what I ended up doing was I had a little portable work light that had 24 LEDs sitting in it, and I said, hey, I wonder if I could use this. So this picture on the right here is, I actually took it apart and kind of rearranged it in a way that would work best with my system, and these actually proved to be even more low power than the original 10 that I had ordered. So I ended up hooking 2 of these up, and they still lasted for about 2 minutes. So now I have a total of 24 on each work light for a total of 48 LEDs. So I was pretty happy about that. Okay, so this is kind of putting it all together. This picture is the arm bracket connected to, sitting on the top of the motor there. This is just all 4 capacitors wired together. So here's a shot of the whole thing. Here's the motor and the arm bracket on the door, and you can see it's wired up to the capacitors here. And then each of these lights are wired separately. They've got about 8 feet of wire on them. So another benefit of using these portable work lights is that they have clips on them and also magnets, so you can hook them on something, or you can stick them on like your fridge or something. I don't know, something that's magnetic. So that was nice portability included there. Obviously, you wouldn't have them sitting in front of the door here because then you can't really open the door. But I put them there for the purpose of taking the picture. And then on the right here, this is just a close-up of the arm bracket and the motor. You can see it's kind of just a bit of a cob job, I guess, because it's got a paper clip kind of holding it all together, and a couple pieces of aluminum that I had to configure. Okay, so now I've got some videos for you. So the first one that I'm going to show you is just of the door opening and closing. So you'll see here just kind of how it turns the motor and sends it back. So there's actually very little turn, but even so I was able to get a decent amount of power out of it. I'll show it again. Just like that. Okay. The next video I want to show you is this is a DMM, which is a piece of equipment that we use to measure the voltage level. So remember, this motor got up to about 24 volts if I was at 19 RPM. Well, over the course of opening the door, it didn't quite get that high, but it got high enough to power the LEDs. So this will kind of show you the speed at which that happens. So it charges up and then very slowly starts discharging. So again, and up in the right here, you can see the reflection of the lights as they come on there. And then, last but not least, I have the actual lights as they charge up at the same time. So they just come up and then very, very slowly, you can't even tell at this time distance that they're discharging. So that's that. so kind of as some conclusions, the biggest room for improvement would probably be the motor. I only utilized about 1/20th of the available torque. It was more a proof of concept rather than maximizing the possibilities that I could do. A better solution would obviously not be to include hot melt glue and sanding, sawing, drilling of aluminum in order to rig this thing up. The LEDs could also be vastly improved. I just kind of took what I had in my room and modified it and used that. Still, a very plausible solution exists, and I think it's a good proof of concept. So acknowledgements, I'd like to thank Dr. Marcus Fries, who couldn't make it today, but he helped with the initial idea. I'd like to thank Daniel Burley for a lot of help with cutting and hacking aluminum and some fun stuff that we did in the machine shop, and of course, Dr. Cornley for taking care of all of us in the engineering department and all that goes on with that. So now I just have a couple of videos that I'll just play. They're a couple minutes long, so you guys can ask questions or whatever during that time, but they just kind of show both the DMM and then the lights as they discharge over a couple minutes. So, thank you.
Questions for Michael?
I have a question. What's kind of your next step? Is there any follow-up with this? Are you exploring, patentability, any of that? Or are you just kind of done and see?
I guess there isn't really a plan as to what I'm going to do next. There's certainly, you could patent like the idea or build a stronger prototype and really maximize this into a product and try and sell it. I don't have it up here, but the cost for just the pieces that I chose came to around $80. So that's, once you maximize that and figure out how you can get that cheaper, certainly you can do a lot better than that. So there is the potential for a product in here, but I guess in answer to your question, I don't really have any plans for a product myself. So.
I have a question. So, did you do patent search for this? And if yes, what did you come up with?
Yeah. The one main patent that is related to this it's a little bit different than what I have here with the, basically it's a patent for generating power from a door like this, but their motor sits inside of the hinge, so whereas mine was just kind of off on an arm bracket, their motor is actually in the hinge, and it's for creating AC current. So you open and close the door, and it takes current both ways. So that was the purpose of that patent. But that was really the closest thing I found.
Did you try this in a pitch dark room, and then was it, I don't know the sense of how bright 48 LEDs would be, bright enough to like put keys into a lock or something like that?
Yeah. These work lights are actually, it's kind of hard to tell from the videos and pictures, but they're actually very directed. So if you had it directed at a light switch or, like you said, a keyhole or something like that, it would be more than enough to light it up. Yeah.
Unfortunately, you have to open the doors first.